1.3, heap property. Now we get to the most important property for the heap data structure, heap property. Yeah. All right. Yeah, because we need to describe a binary tree structure inside a heap. So we want to look at the relationship among heap nodes. All right. Yeah. So we know we need to store a binary tree in an array. Yeah. But actually, you cannot see a visual binary tree. Yeah. So nobody will do it in that way. So visual binary tree, you just see an array. Yeah. So here we need to use some imagination. We need to imagine a binary tree. Okay. Yeah. So then we want to, describe the detailed information in the binary tree. In a binary tree, there are nodes, right? So how do we describe individual nodes? Yeah, so we use a simple way. Yeah. Each node, we just use an array index. Yeah. Because one node and one array index, there is a 1-to-1 correspondence. Okay, 1-to-1 correspondence. Yeah. So if we are given an array index, we know which node it corresponds to. Okay, yeah. If we talk about an array node, then we can quickly connect to its corresponding array index. So that simple relationship. Okay. Yeah. But then next, we need to consider relationship between two nodes. Especially, we want to consider parent-child relationship. Yeah. So in a binary tree, you need to look at parent-child relationship. So how do we describe that parent-child relationship? Yeah. All right. So here, relationship between two nodes can be translated into relationship between two indices. Two indices, yeah. Two locations, two elements corresponding those two indices. Yeah. So that's straightforward connection. Yeah. So now we are ready to describe parent-child relationship. Here, let me draw a general diagram. Yeah. Here, we look at a typical parent-child situation. Yeah. P node, yeah, the parent node, P node, corresponds to index I. Okay, so we use this notation, P:I, yeah, the index I. Then it has the left child node. Its left child, we use L. And which index do we use for its left child? A simple way, 2i. 2i, yeah. So in this way, so we can make arrangement in a perfect way. Yeah, 2i, okay, left child 2i. Yeah. So similarly, the right child, 2i plus 1. So here you can see, this way we'll arrange all the elements, in a really nice way. Yeah. So what do you mean nice way? Yeah. Because we don't want overlap, right? Here, so we don't want, so one node, the index in one node is used by other places. So that's not good. Yeah. So one particular index can only appear in exact one node, yeah, not multiple places. Yeah. So, but here you can see if we use this special way to allocate indexes to the nodes, then all the array elements will be mapped to the nodes in a binary tree. But there is one special point we need to pay attention to. So what's that? The first, the index I cannot be 0. Why? The reason is very simple. If I equals 0, then I and the 2i, they are the same. We do not allow two nodes share the same index. Yeah. So for that reason, I equal this index will not be used in our heap. Okay? Yeah. For that reason. Yeah. Yeah. So A of 0, the first element in the array, is never used for the heap. You can use it for other purpose, so that's fine, but do not use it as any heap node. Yeah. If you follow this simple rule, so then your heap structure will be fine. Yeah. So you will, arrange the nodes, the parent-child relationship, without any problem. Yeah. All right. Yeah. Next, we look at the relationship among heap nodes. Yeah. Or we want to look at the heap property. Yeah. So this is the heap property. Yeah. What kind of heap property we want to have? Yeah. Yeah. First, there are two types of heaps. So basically, so when we organize our data, there are two different types we can do. Okay? The first type called the max heaps. Max heap. So the maximum element is at the root of the heap. Okay? And for the remaining nodes, they will follow some special heap property. Max heap. Yeah. Second type, min heap. The minimum. The minimum element is at the root of the heap. Then for the remaining nodes, they will follow some special heap property. Yeah. So two types of heaps. Yeah. So for the first type, we enforce. Yeah, this property we need to enforce. So we enforce the max heap property for the max heap type. Yeah. Heaps. Okay. So what's the max heap property? The value at the parent, A of I, should be greater or equal to the value of its left child. Okay. Then its value should also be greater or equal to the value of its right child. Okay? Yeah. So the parent node must have a value greater or equal to any of its child, value of its child node. Yeah. If you follow this requirement, then you have a max heap. Similarly, for the min heap, we have the min heap property. Yeah. So we just switch the inequality order. Value of the parent node is less than or equal to any of the value of the child node. Yeah. So that's simple. Yeah. Because these two different heap types are equivalent. Yeah. So here we only need to study one of the two types. The remaining, you can use the simple analogy to derive the similar conclusions. Yeah. So we do not need to spend our time on two essentially same copies. Okay? Yeah. So we just considered the max heap. In all our examples, we assume we work on max heaps. Yeah. All right. So next, now we want to see some example. Yeah. So we want to see the max heap example. Yeah. All right. Yeah. First, look at the simple max heap example. So you can see everywhere you can check the max heap property. Yeah. The value of the parent node greater or equal to the value of any of the child nodes. Okay, yeah. Similarly, everywhere you can check, right? Everywhere you can check. Yeah. If there is no violation in the whole binary tree, whole heap, yeah, so let's just call it a heap, whole heap, then you have a valid maxed heap. Yeah. But after we have a max heap, we need to store it in an array. So we need to look at how do we store these elements in an array, yeah, underlying array storage object for our heap. Yeah. So it's very simple. Yeah. So look at this array. Yeah. The first element, we do not use it. So we leave it blank. Okay? Do not use it for any heap node. Yeah. If you use it for some other information, it's okay, but not for any heap node. Okay? All right. The first node, 16, we put in node with index 1, position number 1. Okay? All right. Then we also know number 2, number 3 with 14 and 10 values. Yeah. Then we store in this way. 14 and 10. Yeah. Position 2 and 3, they are 2 child nodes under the root node. Yeah. That's simple. Yeah. Then we look at a node with position number 2, 2 child node 8 and 7, right? Yeah, values 8 and 7, position number 4 and 5. Yeah. So the relationship like this. Okay. So the next one, node number 3 with value 10, 2 child nodes, 9 and 3 values. Yeah. Like this. Yeah. All right. After that, node with position number 4 with value 8, 2 child nodes with value 2 and 4. Okay? Yeah. So the last one, value 7, its node has only 1 child node with value 1. So like this. Yeah. So in this way, you can see we can store a heap, yeah, in this simple way inside an array. Yeah. Very simple. Yeah. All right. So next, we need to consider another problem. Maintaining the heap property. So when we process dynamic data, we need to do this. We need to maintain the heap property. Yeah. All right. So when the heap property is violated, yeah. So think about when you use a heap to store dynamic data. When new data item comes in, you put somewhere in the heap, then your max heap property could be violated, right? Could be violated. So you need to fix it. Yeah. So you need to fix it. Yeah. Yeah. For that reason, we need to consider this special operation. So we look at the typical portion in the heap. Yeah. So parent node, left child node, right child node. So this in this typical representation. Okay. Yeah. Then we know we consider violations occur locally. Yeah. No matter what kind of violation you have in a heap, yeah, you can find it in a local place like this. Okay? Yeah. All right. So in order to make our discussion a little easier, yeah. So when we do our discussion, we assume the left subtree, it is a max heap. Right subtree also max heap. Okay, yeah. So the only problem we need to fix is in this PLR relationship. Yeah, we need to fix. Yeah. So here we do a local fix operation. Yeah. So what is the detail of the local fix operation? Next slide, we will see the detail. Yeah, we use a pseudocode to write the detail steps. Yeah. And here we just discuss the general idea. Yeah. All right. After we've used the the special fix operation to fix the violation locally, yeah, our step 3, we need to do this local fix globally. Yeah, you need to check everywhere. Yeah, globally. Okay, so to make sure there is no violation in the whole heap. Yeah. Okay. All right. So that's the basic idea. Yeah. All right. So next, I want to describe the local heapify operation. Here we give a name for this operation called a heapify. Okay, heap, make it a heap, heapify operation. Yeah. So this special terminology we use. Yeah. All right. To do that, we use recursion approach. Okay, recursion approach. From beginning to end, recursion approach. Okay, and we consider this general representation between parent-child nodes. Yeah. All right. Now, first, we check the A of I value, compare A of I value and A of 2I value. If A of I is less than A of 2I, we store 2I index in the largest variable. So we use a special variable called the largest. The goal, we want to use largest to store the index that contains the largest value among these 3 nodes. Only these 3 nodes, not other nodes. Yeah. Because we want to do this local heapify operation, not global. Okay? Yeah, only store the largest index among these 3 nodes. Yeah, for the value, largest value. Okay? Largest element, the value of the element. Yeah, for these 3 elements. Yeah, we store the index in this largest variable. Yeah. All right. Else, if A of I greater or equal to 2I, so we just store largest, the index I to the largest variable. Okay, so we check the parent and left child relationship. Okay, we check that, but we also need to check parent and right child. Okay, but parent right child, because this time we have some largest variable stores some index number. Could be I, could be 2I, we don't know. No. All right. So we check A of largest less than or less than the value of A of 2I plus 1. If that happens, we update the largest variable with the value 2I plus 1. Okay? Yeah, because we want to store the index that corresponds to the largest value among the 3 nodes. Yeah. Otherwise, we don't need to change anything, right? Otherwise, we don't need to change anything. Okay? Yeah. So after these if-else statements, you can see the largest variable will contain the index that corresponds to the largest value among the 3 nodes. Yeah. All right. So when we fix it, we try to recover the max heap property. First, we need to check if its value not equal to I or not. If equals I, we do not need to change anything, right? Yep. So the value of the parent already greater than any of the value of each child node. So we don't need to do anything. Okay? But if not I, largest variable does not store I. Okay? In that case, we need to do a swap operation. Swap A of largest and A of I. Swap these two, the values of these two elements. After that swap, we fix this max heap property locally. Only this particular neighborhood. Yeah. After that, then we will do check globally, right? Now we need to do the check globally. And finally, we make sure for the whole heap, this max heap property is enforced. Yeah. All right. So that's our 8.3. Okay. Yeah. Next, we will have the last video. Yeah. So we want to use this max heapify operation to build a heap from any given array. So when we have any given array, it is not necessary, giving us a heap, right? Yeah, it's not necessary, to give us a heap. Yeah. So if it's not a heap, max heap, then we need to apply this max heapify operation in a well-organized way. And then finally, we get a max heap. I just want to use one simple example to show you the whole procedure. So that's simple. All right, so let's start.